Welcome to Lecture 6.2, Spectral Resolutions. Our first task at hand is to establish a fundamental result of self-adjoint linear maps. This is something that I have stated without proof earlier, so it should come as no surprise. Namely, if H is a self-adjoint linear map, then it has only real eigenvalues, and the underlying space X has an orthonormal basis of eigenvectors of H. Now, I want to emphasize the part about it has one. This is not saying that every full set of eigenvectors will be an orthonormal or even orthogonal basis, because we can always scale them, but let's just take H to be the identity map, for example. Every vector is an eigenvector, so you can certainly pick two of them that are not orthogonal, and there's your basis of eigenvectors. So this just says that there is an orthonormal basis. To prove this, we will begin with the first part, that H has only real eigenvalues. And then for the second part, we'll break it into two steps. We'll first show that there are no generalized eigenvectors that are not genuine. I sometimes call these purely generalized eigenvectors. And finally, we will show that eigenvectors corresponding to different eigenvalues are orthogonal. So I'll talk about in a bit why this is sufficient to establishing this. But let's get started with the first part. So why does H have only real eigenvalues? So to show this, it suffices to take an eigenvalue and lambda and show that the complex conjugate of lambda is equal to itself. So to prove this, number one, let's say that we have an eigenvalue of H, so HV equals lambda V for some non-zero V. And what we will do is I will take HV, the inner product of HV with itself, and because H is self-adjoint, the key property is that this is equal to inner product of V with HV. In other words, we can move H from the left and the right side. Normally we have to take the adjoint to do this, but it's self-adjoint. So now, from both of these, we will just convert the H into a lambda and then pull it out. So here we can write this as lambda V dot V. I still use the nice verb dot, even for a generalized inner product. And then I could pull out the lambda to get lambda times V dot V. And then over here, I write V dot lambda V, and I pull out lambda, and I get lambda bar times V dot V. This is a fundamental property of bilinear forms on an inner product space. So now we have these two things. So we have lambda times, well, let me remind you that the norm of V, or the norm squared of V, is V dot V, and since V is non-zero, this is non-zero. So we have lambda times the norm squared of V equals lambda bar times the norm squared of V. Since norm squared of V is non-zero, this tells us right away that lambda equals lambda bar. And that's what we had to show right here. Next, part two. How do we show that H has no purely generalized eigenvectors? So remember what that means. An eigenvector is some vector V such that H minus lambda I times V is equal to 0. And let me call this V1. And a generalized eigenvector is any vector that requires, or purely generalized eigenvector is anyone that requires multiple iterations of H minus lambda I to get sent to 0. So to show that there are no purely generalized eigenvectors, in other words, nothing out here, we have to show that if H minus lambda I to the D, some power D times V equals 0 for a non-zero vector V, then h minus lambda I to the first times v equals 0 for some non-zero v. Okay, so we will do this by induction. We will induct on D, and the base case is when D equals 2. So in this case, let's suppose that we have some vector that gets killed by 2 iterations of h minus lambda I. I claim that it really also gets killed by 1 iteration. So in other words, if h minus lambda I squared times v equals 0, then, well, if this is the 0 vector, then that means that that vector, h minus lambda I squared v dot v, is equal to 0, right? Because we have the inner product of 0 with v. But if h is self-adjoint, then it's clear that h minus lambda I is self-adjoint. I don't think I need to justify that, right? H minus lambda I, the adjoint of this is h star minus lambda I star, and h and I being self-adjoint, h minus lambda I. So in other words, this means, well, I said this is equal to 0. This is equivalent to the inner product of h minus lambda I v with h minus lambda I v being 0. So in other words, I just move one copy of this over to the right-hand side, and this thing right here is the norm squared of h minus lambda I v being 0, and so if this vector has norm 0, that means this thing must be 0, and that's exactly what we wanted to prove, is that h minus lambda I times v equals 0. So that's, well, proof for the base case. So that's the base case. Now suppose, now for the general case, suppose that we have some vd out here that takes d iterations to kill it. So let's write that down. So now suppose that h minus lambda I times d, or to the d, times v equals 0. And what I will do is I will write this as h minus lambda I squared times h minus lambda I to the d minus 2 times v equals 0. So I've just factored it in an obvious way, and now I'm going to call this vector here, h minus lambda I to the d minus 1 times v, I'm going to call this vector w. So now what we have is h minus lambda I squared times w equals 0, and using the base case that we just proved, we know that h minus lambda I to the first times w equals 0. So in other words, we can replace this h minus lambda I squared with an h minus lambda I, and that that means that if we replace, well, how do I, so h minus lambda I times w equals h minus lambda I to the d minus 1 times v equals 0, because again we replaced this squared with just the first. And now, by the induction hypothesis, we can assume, by the induction hypothesis, we can assume that h minus, this result holds for everything less than d. So in other words, h minus lambda I to the v equals 0. And that proves number 2. Okay, so we've proven 1, we've proven 2, and what do we have left? Eigenvectors corresponding to different eigenvalues are orthogonal. I probably could have squeezed the proof of this into the margin of the last slide, but why not just start clean? Okay, for this one, let's say that we have HV equals lambda V and HW equals mu W for non-zero vectors V and W. This is going to be sort of like the first one where we write an inner product. So in this case, it's going to be HV dot W is equal to V dot HW. V dot HW. And then we're going to turn these into eigenvalues, pull them out, and see what happens. So we kind of follow our nose here. So we're here, I'm going to write this is equal to V dot mu W. And I can pull this out. Mu times V dot W. And I don't need to put a bar on this because we know it's a real number. And then over here, I'm going to write this as lambda V dot W and pull the lambda out. So lambda times V dot W. And once again, I'm going to compare what I have right here. So we have lambda times V dot W equals mu times V dot W. Oh, and forgot to emphasize that different eigenvalues, so I should specify that lambda is different than mu. So if lambda and mu are different, that means that V dot W has to be equal to 0. Another way to see this is, in other words, lambda minus mu times V dot W equals 0, and we know that lambda times mu is not equal to 0, so it must be true that V dot W is equal to 0. Okay, so that confirms part 3. Now we have done all 3 of these. And I should probably say a few words about why together this proves that there is an orthonormal basis of eigenvectors of x, because this is a slightly different statement than this last claim up here, but it's not too hard to see why it implies this. So if we take x and we write it as a direct sum of its eigenspaces, something we know we can do from the previous section, let's say e lambda 1 all the way up to e lambda k. So if the dimension of x is n, then k is going to be less than or equal to n because there might be repeated eigenvalues. And let's say that these are distinct lambda i's, and all of these are real as well. So if we just take an orthonormal basis of each one of these eigenspaces, which we know we can do, then I claim that together the union of that is going to be an orthonormal basis of x. And I don't think I'm going to actually write that out because it's going to involve double subscripts, and I think the concept is simple enough. So if I take an orthonormal basis of each of these, then by construction, any two vectors within one of these is going to be unit length and orthogonal. And by part 3, if I take any two vectors from different eigenspaces are going to be unit length and orthogonal as well. So we're going to have n, or a basis of size n. All of them are going to be unit vectors, and by part 3, it's going to be an orthonormal set. Theorem 6.1 that we just proved tells us that every self-adjoint linear map is diagonalizable. In other words, H is equal to P D P inverse. And remember, D is the matrix of eigenvalues, and P is the matrix of eigenvectors, the columns. And because we can find an orthonormal basis, that means that this matrix can be found to have orthonormal columns, and that means that P star P is the identity. And this type of matrix is called a unitary matrix. We usually write it as a U. So a corollary to 6.1 says that any self-adjoint linear map is diagonalizable by a unitary matrix. In other words, H equals U D U star, where U star times U is the identity. So U star is equal to U inverse by this relation. And so you can think of U as it is an isometry. It is a complex rigid motion. So if we draw this commutative diagram that I keep coming back to, so if H is a linear map, and then P is the change of basis matrix, and then so this is with respect to E1 up to En. This is with respect to V1 up to Vn, say. Then upstairs, this is just a diagonal matrix. And you can think of P as a rigid motion. So in other words, applying H is the same as doing a rigid motion P inverse, then applying D, then doing that rigid motion again. Let's continue with assuming that H is a self-adjoint linear map with distinct eigenvalues lambda 1 up to lambda k, and let's write X as the direct sum of the eigenspaces. Remember, E lambda j is the null space of A minus lambda j I. This means that we can write any vector in X uniquely as a sum of vectors in the individual eigenspaces. In other words, X equals x1 up to xk, where xj is in E lambda j. Notice that if we apply H to X, then we get lambda 1 x1 plus ... lambda k xk. For the remainder of this lecture, I will denote the projection of X onto the eigenspace E lambda j by Pj. So Pj of X, which is a sum of eigenvectors, x1 up to xk, is just xj. So it just picks off the jth term of the sum. It is worth noting and reminding ourselves that if we take any two of these orthogonal projection maps, Pi and Pj, and compose them, we get 0. Also, as with any orthogonal projection map, Pi squared equals Pi, and Pi is self-adjoint. Notice that we can write the identity map as the sum of these projection maps. That's easy to see. So I times x is P1 plus Pk times x, which is x1 plus xk equals x. And also H is just a linear combination of these projection maps. We call such a decomposition, this first one, a resolution of the identity. And this next one is the spectral resolution of H. So I say the spectral resolution of H because it involves the eigenspaces of H, and those are uniquely determined. However, I say a resolution of the identity because there's nothing special about these eigenspaces compared to H. They actually, or to I, they came from H. So if we take a different self-adjoint map, we will get a different resolution of the identity. Corollary 6.2, which says that self-adjoint maps are unitarily diagonalizable, can now be restated as follows. if H is a self-adjoint linear map, then there is a resolution of the identity and a spectral resolution of H. Again, all of this follows from because H can be written as E lambda 1, direct sum up to lambda k. So P1 up to pk projects onto these things. Now I want to do an example of this because I really think it helps to motivate how we should be thinking about a result like this. What does it mean that there's a spectral resolution of H? So I'm going to start with a matrix 3, 0, 0, 2, a diagonal matrix, because it can be visualized nicely using our standard basis. So let's take that standard basis. Let's take E1 and E2, and I always like to draw the grid that this determines. So here's that square grid. In other words, this is our coordinate system. And let's apply H. And when we do that, the unit square right here is going to get stretched out by 3 in the x direction and stretched out by 2 in the y direction. And I might over-exaggerate and under-exaggerate just so we can see the rectangles a little more clearly. So here's what that looks like. So you can think about a vector. Let me take this. That doesn't. Let me take the black marker. I think that's going to come out better. Vector v, and let's apply h to v. What happens? So h to v, or h times v, is equal to 3p1 plus 2p2 times v. So it's, in other words, we project it onto the first coordinate and then scale that by 3, and then project it onto the second coordinate and scale that by 2. So we project it onto here, stretch it out by 3, project it onto here, stretch it out by 2. So really, at the end of the day, these squares of side length 1 turn into rectangles of side length 3 and base 3 and height 2. Now just imagine what this would look like if we were in 3-dimensional space and we had 3, 2, 4 as a diagonal matrix. So you can imagine now you have a unit box, and each side gets stretched by a factor of 3, 2, and 4. Or if you want to make these fractions or negatives, you can imagine that they might get squished instead of stretched, or reflected and or stretched or squished as well. But basically we get boxes to boxes. Square boxes to rectangular boxes or prisms. Okay, now let me do another matrix. Let me do up here H equals, this is a matrix I think we had in the previous lecture, 5, -3, -3, 5. And this one, if you remember, had eigenvalues 2 and 8, and eigenvectors 1, 1, -1, 1. And I guess if I want to normalize, if I want this to be an orthonormal matrix, I have to normalize it. So I have to factor it by 1 over root 2. And then I take the transpose over here, 1 over root 2. So I get -1, 1, 1, 1. So what I want you to take from this is that your orthonormal basis are just the normalized versions of these. So let me recreate this same picture down here, but up here. And I will exaggerate because 8, I don't think I'm going to be able to exactly stretch by a factor of 8. So now our basis, this is V1 and this is V2. And this determines a grid. So this determines a coordinate system, which we can visualize with a grid. And now when we apply h to it, I do have more room here. Maybe I will get to stretch by 8. Probably not quite. So v1 gets stretched by a factor of 2. So this is 2v1. And v2 gets stretched by a factor of 8. So imagine that this is a factor of 8. I don't think it's quite that, but I think that's fine. So now our new grid looks like this. So it also consists of rectangles. But basically, the unit square here gets stretched by a factor, let me write this out, this is 8v2, of 2 in this direction and 8 in that direction. So in other words, h times v, if we have some vector up here, v, h times v equals 2p1 v1 plus 8 p2 2, let me fix that, equals 2p1 plus 8 p2 v. And then if we reduce this, this just becomes 2 v1 plus 8 v2. Okay, so the main idea here is that what this is saying, when we have a spectral resolution of H, that means if you take your eigenvector basis, which we always know that you have, take your orthonormal eigenvector basis, then the linear map looks just like these things. In other words, it just literally scales and or stretches each side length by lambda. So a normal linear map, I shouldn't use the word normal, that means something else that we'll get to soon. In other words, if we do this in a standard basis, it will map v1 and v2 to, I don't know, to some parallelogram, some vectors that will define a parallelogram. I don't know which ones, I'm just kind of making this up, but it'll send it. These things generally send squares to parallelograms. Doesn't preserve angles. But what this is saying is, if you take our eigenvector basis, I like to say, if you tilt your head the right way, then every self-adjoint map looks like this. It just takes the unit box and it stretches each coordinate by lambda. So it sends squares to boxes. So these pictures are how I want you to think about self-adjoint map. It's extremely important. One more time, for those sitting in the back, if you tilt your head the right way, any self-adjoint map is just basically a diagonal matrix sending boxes to rectangular prisms. There's one more thing about spectral resolutions that I really want to emphasize, and it's something that we've seen regarding a few other concepts in this class as well. And that is that these things are not all that interesting or deep for finite dimensional vector spaces. I basically just gave you a picture for how to think of them. And again, it's not that surprising when I write things down like this. But the real meat here is how these things are defined in Hilbert spaces. So infinite dimensional inner product spaces of functions that have a few other properties like completeness. So it's a lot more non-trivial that in one of these spaces that there is something called a resolution of the identity or a spectral resolution of an arbitrary linear operator. And now these projection maps are going to involve the inner product, but that's going to involve usually some sort of integral. We've also seen this a little while ago when we talked about how all linear functions or all dual vectors are basically the inner product onto some fixed vector. So basically take our bilinear function x and y and just fix x and plug in, so if you fix one of the coordinates, it becomes linear. And every linear function is like this. That's not all that hard to see if you think about row vectors and column vectors. But in a Hilbert space, this is a very deep theorem. It says every linear function can be thought of as the inner product with some entry fixed. That is called the Riesz representation theorem, and that is a deep theorem in functional analysis. Now, I'm really not going to get into the functional analysis much at all in this class, but I will say that if you want to understand those deep theorems in functional analysis, you really have to master what and why they hold for finite dimensional vector spaces, because that really motivates the concepts in a Hilbert space. I want to conclude this lecture with a key algebraic idea involving spectral resolutions. So I claim that they allow us to define functions on any self-adjoint map. And now what do I mean by this? I mean, if we have a matrix A, I can define A squared, A to the fifth, things like this. If it's invertible, A inverse. So if it's invertible, I can talk about A to the minus 5. Now it's not so clear what the square root of A would be, or if that's even defined. Or what about e to the A, or sine of A? Now, if you've taken a differential equations class, maybe you've seen e to the A for some matrices. It's not clear if this is always going to work, or what it means when it does work. Now, one sort of cop-out explanation for e to the A is, well, you just take the Taylor series of e to the, just take the Taylor series of e to the x and plug in A. In other words, e to the A is I plus A squared over 2 factorial plus A cubed over 3 factorial plus etc. Now, it's not necessarily clear that something like this is always going to converge, or what it means if it does converge. But I claim that if we have a spectral resolution, then any function, any of these functions, and many more, are really easy and natural to define. Okay, let's take a self-adjoint map H and say it has spectral resolution, the sum of lambda j times pj. So even though this is a nice compact notation, I personally like to write things as lambda 1 p1 plus ... lambda k pk. For some reason, this is a little bit psychologically easier to deal with and think about than having this fancy sigma notation. But whatever works for you is great. I will stick with the sigma notation for at least the rest of this lecture, because I don't think any of this is going to be too difficult. Okay, so h squared in this case is just the sum of lambda j squared times pj, and let's think why that is. So, if you take lambda 1 p1 plus lambda k pk and you multiply it by itself, lambda 1 p1 plus lambda k pk, we've already said that all of the pi pj's are going to be 0 if I and j are distinct. So if I and j are distinct. And so this thing here is clearly going to be lambda 1 squared p1 plus ... lambda k pk squared pk. Now this is the algebraic way to think of it. I also still like to think about things geometrically. So if we have this little picture that I don't want to spend too much time on. So remember this grid picture that I drew in the last slide. So this is 3v1, or this is, I should say, 3e1, and this is 2e2, and now you get this grid. So what happens if I take a vector v in here and I apply h? So we project v onto its basis coordinates. So this thing here is p1v and this is p2v. So we project and then we stretch out by 3 and stretch out by 2. So if we do h twice, then we're stretching this out by 9 and stretching this out by 4. And that's exactly what we have here. So I think I get a little bit extra when I see this geometric picture in addition to just this algebraic computation, which is fairly elementary. I get something by thinking about this picture of the boxes and the projection maps. Similarly, h to the m is just the sum of lambda j to the m times pj. And if we take any linear combination of powers of h, in other words, a polynomial p of h, then that's just p of lambda j times capital P of j, again for any polynomial p of t. That's hopefully easy to see. But we can extend this. E to the h is just e to the lambda j times pj, for example. And more generally, if we take any function f of h, as long as it's defined on the eigenvalues. So if our function is f of t equals 1 over t, and one of our eigenvalues is t, or I should say lambda equals 0, then this is not going to work. But otherwise, then we can define f of h to be the sum of f of lambda j to the pj for any function. So this gives us a really easy way to define things like the exponential of a matrix, or the sine or cosine of a matrix, or many other functions that will come up. And again, if you've seen differential equations, if you've taken a differential equations class, I'm sure you have seen things like exponential of a matrix. And more often than not, when you have things like that, you are going to have a self-adjoint linear map. So like often the matrix might be symmetric. Now for a general non-self-adjoint map, you can't necessarily define all of these functions, but again, many of the ones that come up in practice are going to be self-adjoint. Okay, so next time we will talk about a class of linear maps that are said to be normal, and I apologize for the name. It's one of the most overused words in mathematics, that it really has no general meaning other than a very nice class with certain properties. There's normal subgroups, normal maps, normal vectors, etc. But to motivate what these are about, notice that one of the key properties of self-adjoint maps is that they have an orthonormal basis of eigenvectors. So a lot of things we've proven don't really depend on the self-adjoint property as much as the orthonormal basis property. And self-adjoint maps are not the only class of maps we've seen that have this property. So besides self-adjoint maps, we've seen anti-self-adjoint, we've seen orthogonal maps, and we've seen unitary maps. I guess unitary is a generalization of this, I guess, in a complex space. But all of these linear maps have a basis of orthonormal eigenvectors. And normal linear maps is going to be a larger class that's going to encompass all of these. So it's really going to get at what is the technical requirement that is allowing there to be an orthonormal basis of eigenvectors and allowing all of these results that follow from this to hold. So a lot of the things that we have been proving for things like self-adjoint maps or orthogonal maps are going to hold more generally for normal linear maps. So be sure to stick around for that one.